Hello, we are Team XMOS and our project was the Smart Amplifier, audio digital signal processing on an X-Core AI chip. Our technical director for this project was Dr. Andrew Kavanaugh, who is a former URI alum, and the team is composed of myself, a computer engineer, Sahil Chadha, a double major, and Evan Murray, an electrical engineer. XMOS is a semiconductor company that's centered in Bristol, United Kingdom, who specializes in a variety of CPU architectures, with the newest in line being the X-Core AI. Out of the box, it's built to support digital signal processing, artificial intelligence, I/O, and parallel processing through the use of its 16 logical cores, comprised of 2 threads that are 8 cores each. It's used in a variety of multi-channel audio boards and development kits, with the former being especially relevant to our project motivation, which is to eliminate the digital to analog conversion hardware and be able to control the output signal via the DSP of the X-Core chip to drive a Class D amplifier, and more on that later. Showcase the effectiveness of what is called software-controlled hardware, and illustrate the usability of X-Core AI's DSP through AudioWeaver, along with the user-friendliness to be able to create those audio solutions. The anticipated best outcome of this project was to implement that aforementioned Class D amplifier through the use of having the pulse width modulation at the input stage of this amp being controlled by an X-Core AI port. It should be able to accept input from an instrument, in our case it was meant to be a guitar, implementing the digital signal processing through the use of AudioWeaver, which allows digital signal processing concepts to be recognized through the use of block diagrams without needing any prior experience with code. And if we ever got around to it, to be able to create a guitar that would never need tuning. Cutting right to the chase, our anticipated best outcome was only partially achieved. The bright side is, the software was fully completed, the board is able to receive audio input and deliver that pulse width modulation to that output stage using an X-Core port. The specialized components that we would have needed, like the driver speakers and the inductor, are now readily available for us to use. As we said before, the DSP was successfully integrated using AudioWeaver. Beyond just audio effects, we were able to use dithering and pitch correction algorithms. And the schematics have a 1/4-inch guitar input jack in mind, and the input stage is a pickup preamp for the pickup signals being too small to be regularly processed by the ADC. The downside is, due to complications with the PCB manufacturing companies, we were never able to get actual hardware to be able to test those components. Moving forward into our key technical accomplishments though, we were able to design X-Core programs that can communicate in parallel and generate timing diagrams for testing, which we were able to use to verify that our output stage software was successfully completed. Additionally, the schematics for the new input and output stages of our PCB were successfully created, and we were able to use SPICE simulations as shown to the right to verify their authenticity. The economic impact of this project for XMOS is the elimination of a digital to analog converter can make the PCBs have a better cost efficiency, since those components tend to be relatively costly, as well as the ability to design custom audio boards, all of which implement this Class D amplifier design, since it will be broken down to such a generic digital to analog audio component that it could be used for a variety of solutions. It will also increase XMOS's brand recognition in digital signal processing applications and even high fidelity audio. Here is the block diagram showcasing this process. Note that a guitar signal is mono, so at the very end of that output stage where there's the Class D amplifier and the speaker, we would only need to implement one of those components, which we did. Moving on to my individual technical contributions, I was able to contribute to the DSP by creating a couple AudioWeaver effects, most notably reverb and delay. I finalized the input and output stage schematic designs, and most importantly, I successfully completed the source code for the output stage. It runs in parallel with the I2S sample serial to serialization to be able to catch PCM samples and send them out in time to not disrupt the scheduling to what would regularly be going to the DAC. And once it processes those samples, it transforms them into PWM and then sends them to the I/O port. Here is a block diagram of one of the AudioWeaver components that I made, in this case the dual channel reverb. And here's a little block diagram showcasing how the PCM to PWM process works. We start in process 1, where it gets a PCM sample from the I2S or the USB mechanism. It sends that sample to be processed to AudioWeaver, and upon its return, it sends that sample to process 2, which transforms it into the PWM, before scheduling the next process to get the next PCM sample, and it keeps doing this forever. After initializing the port and the buffer clock, the sample from process 1 is caught, and then it divides by the maximum ADC value to be able to get a value for the duty cycle, and in accordance with that duty cycle, it buffers out zeros and ones to accurately represent that PCM sample in pulse width. And here are the two block diagrams for the input and the output stage. Note that the input stage schematic has the aforementioned preamp module, and in the output stage, the input for the gate driver is received from the Xcore port, which gets the PWM sample that we created from the ADC PCM sample. And here is a bunch of console prints for what the PWM ports look like at each interval once they're received. I flipped it around sideways so it's easier to visualize the sine wave in pulse width. And on the bottom is the VCD timing diagram to represent what that port was observing once the software ran. Just for comparison, I had an actual sine to PWM diagram. And notice how at the higher amplitudes the pulse width gets wider at output high intervals, and in lower amplitudes the output low is wider, which accurately matches what we have here for the 1 kHz sine wave, verifying that our software is functional. I will now pass it over to the second designer, Evan Murray, for him to talk about his technical contributions.
Hello, I'm Evan Murray and I'll go over my technical contributions. So for the project, I worked on the Class D amplifier stage, some audio effects, and the overall casing for our amplifier. Here's the Class D amplifier contributions. I contributed to the half bridge and full bridge Class D amplifier simulations in LT Spice. So here you can see a LT Spice simulation for the Class D amplifier where I created a comparator to create our original PWM signal, and it's sent through to our Class D amplifier where we're able to validate that the PWM is being amplified and a low pass filter to retrieve our analog output signal. Next, I worked on a Fusion 360 amplifier housing design. So this is measurement specific to our board, and all that's left to do is when our PCB is delivered to take the measurements of the heights of ports and make holes in the design that we have. And also selected 8 ohm and 16 ohm speaker drivers for our project. Another contribution is I worked on our anticipated best outcome of having an auto-tuned guitar. So first I created a proof of concept MATLAB file where I loaded in an audio sample. It's converted to mono and downsampled. And then with that, we can use a pitch detection function within MATLAB. And once we have pitches in different segments of audio, we compare it to guitar frequencies. And we compute the semitone difference between our detected pitch and the target pitch. And then we can do a pitch shift and finally output the audio and listen to an auto-tune version of our guitar sample. So this MATLAB version was a proof of concept, and so I moved on to a more complicated advanced algorithm. This algorithm is straight from the patent for auto-tune. It takes in the audio and is after a similar algorithm as the MATLAB version. It runs through different candidate lag values with this energy function of the signal and a cross correlation function. And it turns out that with this function, you can determine whether a tested lag value is a period of your audio. And then through a simple conversion, you can convert that lag into the frequency that's detected. So this verified that we could create a working version of pitch detection without using MATLAB built-in functions. Next, I'll pass it off to Sahil.
Hello, I am Sahil Chada, the double major on this project. I'd like to once again briefly revisit the block diagram to refresh the audience about the goals of this project design. I'll now go over my technical accomplishments. So far, my focus has been mainly on the reconfiguration of the PCB. The original multi-channel audio board provided by XMOS was used as the base and was heavily modified throughout the course of this project. Since the focus of the project is fairly specific in regards to the removal of the digital to audio converters in favor of a Class D amplifier and completely software-based digital signal processing, a number of components on the multi-channel audio board were redundant and therefore removed. For example, this project will only take input from a guitar, and therefore the MIDI, coax, and optical inputs were considered futile and removed. The clocks that were previously present on the board to generate different clocks for different components were replaced with a single 24 MHz clock. The entire XS2 JTAG system has been replaced with an external JTAG, connected to the board with a single jumper while still enabling the use of Xscope, a debugging system for programs using Xcore AI. That can be seen right over here. And right here, this is the J101 jumper that will be used to connect the external board to this board right here. All the DACs were removed, and since the system is only using a single input, only one ADC has remained. Now, along with these changes came the replacement of the main XMOS chip. The original multi-channel audio board design took advantage of a 128-pin XMOS chip, which held enough pins for all the various components and signals of the board. However, with the simplification of the board, the number of pins required were significantly lowered and drastically reduced, allowing for a larger chip to be replaced with a smaller 60-pin XMOS chip. A port map was created and used to ensure that the ports were capable of transferring signals with certain bit lengths. Furthermore, a number of components were added, which also need to be compatible with the remaining pins on the chip. These components included an input stage and output stage, which Ahmed and Evan had discussed earlier, and multiple level shifters and jumpers for various new connections. The 60-pin chip sends signals at a 1.8 volt logic level, whereas the majority of the components operate at a 3.3 volt logic level, so level shifters were implemented to keep the integrity of the signal the same, while also raising the voltage levels of the signals to match those of various ICs across the board. That can be seen right over here. So these are the level shifters on the board, and this is the actual 60-pin chip itself. And these will send the signals to the level shifters using multiple pulled up resistors, and then will be sent to various components along the board. The board has been designed as an amplifier for a guitar, meaning it will need to supply enough power to take input from the guitar pickups, drive the amplifier that we have implemented in the inputs or the output stage to the desired levels. As such, a new power supply was chosen, which supplies 12 volt, 24 volt, 12 volt, negative 12 volt, and 5 volt to the board. And that will replace the 12 volt input that the original multi-channel audio board acquired from the USB. These new additions meant that a schematic symbol and a PCB footprint were designed and implemented for the connecting jumper and will be compatible with the buck converters already present from the board. This can be seen right here. This is the new jumper for the connector for the new power supply, supplying rails for 5 volts, 24 volts, 12 volts, and negative 12 volts, respectively. Now, power distribution from the board is handled through a combination of polygons and split planes. The split planes are located on the third layer, also known as the power layer, and consist of planes for 0.9 volts, which is along the inside of the 60-pin chip, a 1.8 volt rail, or 1.8 volt plane, which is around the chip, and also for a number of the 1.8 volt signals going to the level shifters and the resistors. 3.3 volts, which most of the components will require. 5 volts, 12 volts, negative 12 volts, and 24 volts. Most of the planes will be supplied by thick traces stemming from the power supply connector, which I showed earlier, but the rest of the connections will simply require a multi-layer via to receive power. The concern of impedance mismatching can be eliminated, as the signal paths that will be affected are all on the top layer. those signals being those acquired from the USB input right here. And those will be referenced to the ground layer, since those signals that are traversing across the top layer, and the layer below that is the second layer of the ground layer, and then comes the power layer. This way, power can be successfully distributed to all components despite the multitude of voltage levels required. Other than the PCB, I also developed a number of audio weaver models for various guitar effects. These models include both the phaser and compression models, and the phaser one you can see right up here, as well as the universal model for implementing dithering, which is the introduction of noise to reduce quantization error accrued during upsampling. As a signal is upsampled and quantized, the error will be reduced by the noise, since those samples will be duplicated, after which the noise will be upshifted to a higher frequency and filtered out for the final audio signal. This dither model is implemented at the start of each audio weaver design, and will be implemented across the board through all of our audio weaver designs. This will conclude my technical accomplishments for the project. Finally, the team would like to acknowledge the team of directors that allowed this project to be possible. Our technical director, Andrew Kavanaugh, our consulting director, Mike Smith, and the program director, Harish Sunak, have all been paramount in the progress of this project, and we cannot thank them enough. That's all from the XMOS Smart Amplifier team. Thank you for your time.